So let's look at the following limit. Limit as x approaches 0 from the right of sine of 1 over x. And just like with any limit, the first thing we should try to do is plug in whatever x is approaching. It's not going to work. We're getting sine of 1 over 0. And that is, I don't know what that is. It might not approach anything. What we can do is, there's actually a way of kind of seeing that this oscillates infinitely back and forth between -1 and 1 and 0. So I could pick values of x that are closer and closer to 1, like the following. Like the following, James, yeah. Like 2 over pi and 2 over 3 pi and 2 over 5 pi. So let me ask you a question. Are these numbers getting smaller? Okay. The denominator is getting larger. The numbers are getting smaller. So I'm just doing 2 divided by every odd multiple of pi. But look what happens when I try and evaluate this function at each of those odd multiples of pi. Sine of 1 over 2 over pi is sine of pi over 2. Right, when you divide by a fraction, you flip and multiply. And so sine of pi over 2 is 1. And sine of 1 over 2 over 3 pi is the same as sine of 3 pi divided by 2, which is -1. And if I keep going, 2 over 5 pi, the reciprocal of that is 5 pi over 2. And 5 pi over 2 is coterminal with pi over 2. It's really pi over 2 plus a full revolution. Pi over 2 plus 2 pi. That's going to give me the same sign value of +1. So we're at the top of the unit circle. And down here at, say, 2 over 7 pi, which is taking sine of 7 pi over 2, I'm going to get -1. Because again, that's really just 3 pi over 2 plus another 2 pi. Or plus another 4 pi over 2. I could do this literally forever. Right? This list isn't ending. I can do 2 over 13 pi, 2 over 15 pi, et cetera, et cetera, et cetera. So I can find an infinite number of positive numbers getting closer and closer and closer to 0 so that the sign values go back and forth between 1 and -1. Graphically, here's what this is kind of looking like. If this is, say, 2 over pi, which is a little bit less, it's like 2/3, my value is, I should make it bigger here. My value is 1. And then say 2 over 3 pi, which is like 2 over 9, so much smaller, I'm getting -1. And then 2 over 5 pi, which is even much smaller, I'm getting +1. And the 2 over 7 pi. So you can see I'm going to go back and forth between these values an infinite number of times. So I tried to graph this, it'd be something like this. It'd be terrible. And I would have to do this forever. The limit doesn't exist. We are oscillating an infinite number of times between -1 and 1 as x gets closer and closer and closer to 0. So this limit, as x approaches 0 from the right of sine of 1 over x, does not exist. And typically I would say the 2 different ways a limit does not exist usually are either if you have 2 different sides approaching different values, or you have a limit that's oscillating back and forth between different values. If either of those things happen, our limit does not exist. Now, that said, we can still deal with some limits that have this sort of expression involved in them. For example, I'll change it up just a little bit. No, I'll do, you might have already seen this example. It's a pretty standard example. Let's look at the limit as x approaches 0 of x squared times sine of 1 over x. We're going to talk about how this limit actually does exist, even though part of it is doing some wild oscillating thing. Here's the idea. Sine of anything, doesn't matter what you're taking sine of, is always bounded. Sine of whatever is always between negative 1 and 1. Doesn't matter what you're taking sine of. It could be a super gross thing in there, argument in there. In this case, it's 1 over x. And when we have a compound inequality like this, the idea often is that we're trying to move towards using the squeeze theorem to talk about as we do this problem. So I would really love to be able to take the limit of this, but to do that, what I'm going to do is make the middle part here look like that. So I'm going to multiply by x squared, but I can't just do that to one part. I have to do it to the entire thing. Now, fortunately, x squared is always non-negative, so I don't have to worry about the inequality changing directions. Right? If I was multiplying by a negative thing, I might have to change the order of the inequality. Not a worry here. If I multiply by x squared, you get negative 1 times x squared less than or equal to x squared times sine of 1 over x less than or equal to positive x squared. Or more succinctly written, negative x squared less than or equal to x squared times sine of 1 over x less than or equal to positive x squared. Here is where the squeeze theorem comes into play, and what the squeeze theorem says. So the squeeze theorem says that if you take the limit of these two outer things, and it's the same. So the limit as x approaches 0 of positive x squared is 0 squared, which is 0. And the limit as x approaches 0 of negative x squared is negative 0 squared, which is 0. Since x squared times sine of x is less than or equal to x squared, and x squared times sine of x is bigger than or equal to negative x squared, and both of those things are getting closer and closer to 0, the limit of sine of x has to be less than or equal to 0 and bigger than or equal to 0. And if you're less than or equal to something and bigger than or equal to that same something, there's only one thing you get to be, whatever that something is. Graphically, sorry, 1 second. Here's how things look graphically. Sorry, a new one here. So if we look at the graph of y equals x squared and the graph of y equals negative x squared, we can see that, oh yeah, if something was between them, it's going to get smushed to 0 as we get closer and closer to 0. And if we actually graph y equal to x squared times sine of 1 over x, we can see that, oh yeah, that green function is always between the red function and the blue function. Since the red function and the blue function, bless you, are getting closer and closer to 0, this thing, although it's still bouncing back and forth, back and forth, back and forth, they're getting squeezed together. So the sine of the x squared times sine of 1 over x function has to get squeezed to the same value that they're both getting closer and closer to. It's kind of like a sieve. I never pronounced that word correctly, or a funnel, like they're getting funneled into the same thing. It's kind of neat. So if I was actually like writing this as an answer to a question, I would say by the squeeze theorem or sandwich theorem or whatever other name you prefer to call it by, the limit as x approaches 0 of x squared times sine of 1 over x is also equal to 0. But it's definitely relying upon the fact that we showed that the limit of the thing it was less than and the limit of the thing it was bigger than were both equal to the same value. Oh, yeah, there's so many different things to talk about. Let's see here. Let me look at one thing real quick here. Yeah. Okay, we should do that. Cool. We talked about 0 over 0 limits last time. Not that that's all of them, but it's a large swath of them. We still need to talk about the precise definition of the limit. We probably need to talk about limits that go to infinity and also end up being infinity. So those are also kind of on the list. We did one example of those at the very end of class last time, but I feel like we should probably spend some time with the precise definition of them because that's certainly, it's a big deal. Everyone, and it's kind of on everyone's mind. So I would say, for those of you that might be math majors, which there are probably not a lot of, this delta epsilon idea is going to persist throughout your career as a math major. For those of you that are not math majors, which is probably most of you, you probably won't see this much after this class. You might see it again in 21B or 21C. Probably won't. People might allude to it, but the rigor of it will probably be just in 21A, and then it'll kind of go away. That said, we still need to learn it. So let's talk about, where do I want to start here? Yeah, I like this example. So let's start with the following. So let's see, let's write this. So the precise definition of, so we're talking about the limit as x approaches a of f of x being equal to L. And what we should see when we read this is what we're saying is that as x gets close to a, f of x gets close to the value L. That's the whole idea summed up in words. Now we're going to make it more mathematically rigorous as we go along here. But when we get to the mathematical rigor part, we start using deltas and epsilons and all that jazz. We're going to take it back and say like, oh yeah, but what we really mean is just x is getting close to this number and the function's getting close to this y value. That's all we're really going to mean. But let's build up to it. So let's start with the following. We're going to sketch the portion of f of x equal to 2x plus 1, where firstly, absolute value of f of x minus 7 is less than, I don't know if I love 1 here, but we'll find, we'll go with 1. I'll say 1/2. And probably the easiest way to do this is just to kind of solve for things. So when you have an absolute value inequality, the insides have to be, well, here, whatever's inside here has to be either less than 1/2 if it's a positive number, or bigger than 1/2 if it's a negative number, right? You can have like negative 1/4 because the absolute value of negative 1/4 is positive 1/4, and that's still less than 1/2. But if we were too negative, that'd be a problem. If the insides were like -3, yeah, -3 is less than 1/2, but the absolute value of -3 is what? And that's bigger than 1/2, so we can't be too negative. So here what we need to say is the inside part of the absolute value there, or the argument of the absolute value, has to be between -1/2 and +1/2. And then if I add 7 to both sides, to all sides, I should say there's more than 2 sides. If I add 7 to all sides, 7 plus 1/2 is 7.5. 7 minus 1/2 is 6.5. So graphically, here's how this looks. I'm gonna do my best here. The graph of 2x plus 1 is a straight line. And I guess I'm going to draw and dash the parts I don't want. I'll fill in the parts I do want. So here's my line. F of x equal to 2x plus 1. And I want everything within 1/2 above 7. So up to 7.5. So I'm not including 7.5. And down below to 6.5. So I want this portion of the graph. That portion of the graph has the y values I am looking for. Cool. Okay. It's going to feel a little bit repetitive for a minute here. That's okay. Sometimes it's good to repeat things. So I will point out this segment has all y values within 0.5 of y equal to 7. Okay, part B. We also want to look at where, or to graph the portion where the absolute value of x minus 3 is less than 1/4. Okay, well, again, same idea. We're going to say that absolute value of x minus 3 less than 1/4. You can rewrite that as x minus 3 being between 1/4 and negative 1/4. And if I add 3 to all sides, I'm going to get x between, I could write 3 plus 1/4, or I could write 13/4. I really don't encourage you to write 3 and a fourth, meaning, I think, right, we typically, we don't like this. And the reason why we don't like this is because if I was going to write 3 times 1/4, that's how I would write it. Right? 3 times 1/4, I might write a little dot there, right? But that means a different thing than that. This means 3 plus 1/4. This means 3 times 1/4. They're very, very different values. So we typically don't like what we call mixed fractions. This is usually a no-go. Instead, we would rather write 3 plus 1/4, or I would probably just change it to decimals if it's easy to, and write it as 3.25. That's not always easy to do, right? Some decimals don't end, but most of the time, decimals are okay. I'm gonna write this as x between 3.25 and 2.75. And I'm gonna graph. Try and make my graph look as similar as I can. This is still f of x equal to 2x plus 1. And trying to line things up here because we're going to see something here. Let's say that's x equal to 3. So here's 3 1/4. Sorry, there's 2 3/4. There's 3 1/4. So we're getting this portion of the graph. And at least from the way I've drawn things, it looks like those could be pretty similar. Right? I'm sorry, you can't quite see all of that. Now you can. It looks like those might be very much the same. But let's observe that they actually are the same. So let's see that they're the same by pointing out that if you look at f of 3, f of 3 is 2 times 3 plus 1, which is 7. F of 3.25 is 2 times 3.25 plus 1, which is 6.5 plus 1, which is 7.5. And f of 2.75 is 2 times 2.75 plus 1, which is 5.5 plus 1, which is 6.5. So this point here has a y value of 6.5. This point here has a y value of 7.5. So we can describe the same piece of this graph by either talking about a domain for the x values or a range for the y values. And either way, we can kind of describe the same piece of this. Now, what if we wanted to instead make how far we were from 7 a little bit smaller? Right, instead of saying I want to be within 1/2 of 7 on either side, I want to be within, say, I don't know, 1/10. So suppose we want to be within 1/10 of y equal to 7 on the graph of f of x equal to 2x plus 1. Can we find the x values that are going to describe that? Well, do it. So I want to be within 1/10 of y equals 7. So I want the absolute value of f of x minus 7 to be less than 1/10. Again, graphically, here's what we're saying. Here's 7, and I'm going to draw this kind of exaggerated so it's easier to see. Here's 7 plus 1/10. Here's 7 minus 1/10. Yeah, I know I could write 7.1 and 6.9, but I wanted to write it this way. So I'm looking for the corresponding x values that are on either side of 3. Here's how I'm going to do it. Here's kind of the standard way of doing it. Take this inequality and replace f of x with what f of x is actually equal to. So I'm going to rewrite this as the absolute value of 2x plus 1 minus 7 less than 1/10. And I'm going to simplify. I'm going to write this as the absolute value of 2x minus 6 less than 1/10. I can factor out a 2. Now here's the fun part about absolute values. I'm going to factor out a 2 and write the absolute value of 2 times x minus 3. And then the absolute value of a product is the product of the absolute values. What do I mean by that? I mean literally, so like for example, if I said, what's the absolute value of 3 times -5? Sure, you could say it's 15 by doing 3 times -5, which is -15, absolutely. But you could also break it up as the absolute value of 3 times the absolute value of -5. That would also work, and you would still get 3 times 5, which is 15. The reason I point this out is because it's not a big deal here. But later on, when you have like a -2 getting factored out, and then you pull it outside of the absolute value, it's going to become a +2 because you have to take the absolute value of it. So I'm going to write this as the absolute value of 2 times the absolute value of x minus 3. But then the absolute value of 2 is just 2. So this is going to become the absolute value of x minus 3 is less than 1/10 divided by 2, which is 1/20. So I need x minus 3 to be less than 1/20, bigger than -1/20. So x needs to be between 3 plus 1/20 and 3 minus 1/20. So that's the interval I need to be from 3 minus 1/20 to 3 plus 1/20. And the thing we actually really care about here is how far away from the middle, from 3 are we? Well, on either side, we have to be within 1/20th. So what we would say here is that we need delta to equal 1/20th. So that if the absolute value of x minus 3 is less than our delta value of 1/20th, or in other words, if x is really close to 3, how close to 3? Within 1/20th. If x is within 1/20th of 3, then we can guarantee that f of x is within 1/10 of 7. Or in other words, if x is close enough to 3, then we can make sure that f of x is as close to 7 as we desire. That's kind of really, I mean, there's a lot more to it still, but that's the general idea. We want to find how close x needs to be to the thing that x is approaching, so that f of x is as close to the limit value as we want it to be. We're deciding how close we want to be close to the limit, and then we're finding how close we need to be based on that for x to be close to the value approaching. That's what we're doing. And then we're going to stop using actual numbers, and we're going to start using epsilons and deltas. So We're going to generalize this example. We're going to generalize and show that the limit as x approaches 3 of 2x plus 1 is equal to 7 by showing the following. By showing that if, okay, here's the part where I'm going to write math and I'm going to say words. If x is really close to 3, that's what I just said. If x is really close to 3. Then f of x is close to the limit 7. Sorry, I should have written 7 there, not L, but I made a mistake. So that's the idea. We're going to show that if you can get close enough to 3, then the function can be as close to the limit as we want. How close? Epsilon close. And generally, when you hear the word or letter epsilon, which is like a lowercase epsilon, you should think, oh, that's a small positive number. Same for delta. When you think about delta and epsilon, you should think, oh, those are small positive numbers. They do need to be positive, even though sometimes you write negative things. Just, they do need to be positive. So I say so a lot. So here's how we do it. We're going to start with what we want. We're going to start with, we want the absolute value of f of x minus L be less than epsilon. And I'll point out that epsilon is positive. Okay, that's a little more general than I probably want to start with. I really should probably write my function in there and my limit value and work with that. So what I really want is the absolute value of 2x plus 1 minus 7 to be less than epsilon. And then what I'm going to work towards the absolute value of x minus 3 less than some delta. Where delta is usually defined in terms of epsilon. We often say that given we want the absolute value of f of x minus L to be less than delta, given that we want the absolute value of f of x minus L to be less than epsilon, we're going to find a corresponding delta. So the delta we're finding depends on whatever epsilon happens to be. So let's do it. We're going to do a little bit of algebra. We're going to get the absolute value of 2x minus 6 less than epsilon. We're going to factor out the 2 just like we did before. And get 2 times the absolute value of x minus 3 less than epsilon. And then we're going to get the absolute value of x minus 3 less than epsilon over 2. And that is our choice for delta. Which makes sense if you think about our previous examples. In our first example, sorry, all thumbs here. We started with wanting f of x minus 7 and absolute value to be less than 1/2, and we got our delta to be half of that. Our delta was a 1/4. And in the next one, we started with wanting epsilon to be 1/10, and we got our corresponding delta to be half of that, 1/20. And this is true for this example. Whatever your epsilon is, we need delta to be exactly half of that so that things work the way we want them to. So that if x is really, really close to 3, our function will be really, really close to 7. Yeah. So we're going to choose delta equal to epsilon over 2. We've done all the mathematical work writing the proof is a whole other animal. So here's how we're going to write the proof. And you might just want to watch this for a minute, although you're always welcome to write things down. But I want you to see what we're going to do. So here is our proof that the limit as x approaches 3 of 2x plus 1 equals 7. So when I write these delta epsilon proofs, and people have their own styles, you can do what you want. But here's what I would say people often do when they write proofs like this. You tell them what you're going to tell them, then you tell them, then you tell them what you told them. So I'm going to start off by saying, this is what I want to do. Then I'm going to show you how I did it. Then I'm going to say I did the thing I was trying to do, which seems a lot like overkill, but it gets the point across. So here's what I mean. I want to prove this limit is true. So I want to show, and I need to back up. It's been a few years since I've done this. Just to make sure I'm saying all the things. Yeah. So I'm going to start off by saying for any epsilon greater than 0, because we have to say that epsilon is positive. My proof. We want to find a corresponding delta such that, okay, here's the kind of the big deal. If the absolute value of x minus 3 is less than delta, then the absolute value of 2x plus 1 minus 7 is less than epsilon. That's what we want to do, because that would show that the limit is what we think it is, right? It's showing, right? All this really says again is, let me write it over here, right? All this really says is that if x is really close to 3, if we make x close enough to 3, then we can get f of x close to 7. As close to 7 as we want. How close? 1/1000th, 1/1,000,000th, 1/1,000,000,000th, as close as you want. That's the point, is that whatever epsilon is, whatever small, tiny, positive number the epsilon is, we can always get within that, whatever, I can't think of the right word. We can get within that measure. That's probably not the best way to say it, but we can get as close as we want. Okay, now we're going to do it. So we're going to choose delta equal to epsilon over 2. And then depending on how much work you want to show, it's easier for ones like this that are linear. When they're non-linear, we often kind of be like, well, look at the work I did, and then we see the thing we did. But for now, I'm saying choose delta equal to epsilon over 2. Then the absolute value of x minus 3 less than epsilon over 2 implies that 2 times the absolute value of x minus 3 is less than epsilon, which implies that the absolute value of 2x minus 6 is less than epsilon, implies that the absolute value of 2x plus 1 minus 7 is less than epsilon. As desired. We started off by saying the x was really, really close to 3, right? This part here really is saying that x is between 3 plus epsilon over 2 and 3 minus epsilon over 2. So if epsilon is small, then we're not a lot bigger than 3, we're not a lot smaller than 3. And then we're getting to say, because of this, this has to be true, this has to be true, this has to be true. So then we're saying, oh, look, f of x is really, really close to 7. Here we're saying 2x plus 1 is less than 7 plus epsilon is bigger than 7 minus epsilon. And then personally, I like to then sum it up or wrap it up by saying, thus, I like the word thus. Thus, we have shown or proved that the limit as x approaches 3 of 2x plus 1 is equal to 7. Is it more words than you might actually need? Probably. Do I like it? Yeah, I like, but again, you can write it. Like, let me just show you. We'll do another one, and I'll try to write the proof in a more abbreviated way. But this is the idea. This is probably what your instructor is looking for as far as writing the proof. Let's look at, should we do one more linear example? The linear examples get to be pretty easy to see what's going to happen. But let's look at one more example. That's linear before we do some non-linear examples. And I'll try to write this next proof in a more abbreviated way. So let's say that we want to prove that the limit as x approaches 2 of negative 5x plus 13 is equal to 3. Most of these limits would be easy to evaluate, right? If I just gave you that limit, you could evaluate it by substituting in 2 for x and getting negative 10 plus 13, which is 3. These aren't meant to be limits that are hard to see what they're equal to. They're meant to be that we're going to take the time to actually prove with the precise definition of the limit that they are what we say they are. Okay, so here is where I'm going to start. And this is, I would kind of say that this work I'm about to do here is what I think of as the side work or the scratch work. Here's my scratch work. In fact, I'm going to make you all do it. I'm going to start with this. The absolute value of f of x minus L less than epsilon, which in this case is the absolute value of negative 5x plus 13 minus 3 less than epsilon. I want you to do the algebra necessary to get to a place where you have the absolute value of x minus 2 less than something. Probably epsilon divided by some number. I'll remind you that whatever you have over here has to be positive, and epsilon is already positive. So do what you need to do. Do some subtracting, factor something out, bring it outside of the absolute value, divide by it, and see what you get for epsilon divided by something. All right, let's see what we get. Simplifying this, I have the absolute value of negative 5x plus 13 minus 3 is plus 10 less than epsilon. I'm going to factor out a negative 5, but I'm going to be extra careful. That negative 5 is still inside the absolute value. I'm left with an x minus 2. And then when I bring the absolute value, when I bring the negative 5 outside, it becomes positive 5. So this is going to turn into positive 5 times the absolute value of x minus 2, less than epsilon. Yeah, I'm skipping the step where I write it as the absolute value of negative 5 times the absolute value of x minus 2, because we know that the absolute value of negative 5 is going to be positive 5. And then finally, dividing both sides by 5, we get that the absolute value of x minus 2 needs to be less than epsilon over 5. So that's what we're going to do when we write our proof. We're going to pick delta to equal epsilon over 5. That's our choice. Okay, so now, how am I going to write this in a more concise way? Very carefully. Yeah. Sure, I can write this a little more concisely. So proof. I'm always starting my proofs by saying, let epsilon be greater than 0. That is almost always the first thing we have to say. Let epsilon be greater than 0. We want, or I want either way, to find a corresponding delta also greater than 0, such that if the absolute value of x minus 2 is less than epsilon over 5, then the absolute value of negative 5x plus 13 minus 3 is less than epsilon. Again, like before, pick delta equal to the thing that we found we wanted to be equal to. Epsilon over 5. I like to say the things I've done, but you can either write something like, then by the work shown above, or then you can really just say, then if the absolute value of x minus 2 is less than epsilon over 5, I don't really think that then there's necessary. Then we can conclude that the absolute value of negative 5x plus 13 minus 3 is less than epsilon. That always feels a little hand wavy to me. I'm like, yeah, I know I just showed it up above there, but I still feel like I should have said more. But I didn't want to, because writing lots of things is never what we really want to do. Therefore, or thus, whatever you like, we have shown what we wanted to show. We have proved that the limit x approaches 2 of negative 5x plus 13 is in fact equal to 3. So again, right, I started with letting epsilon be greater than 0. I said we want to find a delta so that the thing that we want to be true is true, right? We're always trying to show that if x is really, really close to what x is approaching, everyone should be looking up here, then f of x is really, really close to what its limit value is. That's the whole idea. The difference between x and 2 is small. The difference between f of x and its limit is also small. That's another way of saying that things are close to each other, is if their difference is small. Questions so far? I think I have some handouts somewhere that have some good like fill in the blanks. I'll try to find those and post them on Canvas so you can take a look at them, because I think they're good practice. Really, to be able to do this, you have to practice writing these things down. Like you have to practice actually writing these words. Be like, okay, I know how this flows. It kind of feels like you're copying someone else's work almost. Like you're like, I'm just gonna write the same words that someone else wrote and fill in different functions. But that's kind of how it goes. One thing you might notice after you've done this for a while is that for anything that's linear, that your delta ends up being just equal to epsilon divided by whatever the absolute value of the slope is. So in the first one, our slope was 2, and our delta was epsilon over 2. In the second one, our slope was negative 5, and our delta was epsilon divided by positive 5. That is not a coincidence. It always ends up happening that way. Things get more complicated when the functions are non-linear. And I believe everyone in their class, so I don't think I saw from the notes no one's doing the thing where like the teacher says, let delta be less than 1. And then we work on like, they're doing the thing where like they find two inequalities and they're like, oh my gosh, they're like x is between these two things and these two things, and then they set the two things like equal to each other. That sounds vaguely familiar. Maybe I'm not doing a very good job. I think that's what I've seen. Let's do one and then we'll talk about if something else is happening. And I'm pretty sure that's the way there's two different kind of ways of approaching nonlinear things, and the older textbook used to do it a different way, and some professors have still hung on to that method at UC Davis, so sometimes that way gets taught. I'm not a fan. I like the newer way. The newer way, even though I learned it the older way, I think the newer way makes a little bit more sense, in my opinion. So let's talk about what we do when things are nonlinear. The end of the day, the process is still kind of the same. It's not so much that we're doing something more, it's actually that the ones we just did, we're kind of taking shortcuts. What I really, in fact, let's go back for a sec. Excuse me, let's go back for a second. And I'll talk about the shortcuts I'm doing with this scratch work here. Sorry, I'm not like, so this scratch work here, I'm going to show you the shortcuts I'm actually using, and then we can talk about how we're going to do for the actual problem. So really what I'm doing here is I'm saying, I want this to be true. So I want the absolute value of negative 5x plus 10 to be less than epsilon. If I write that out long ways, that's negative 5x plus 10 between epsilon and negative epsilon. Then you subtract 10 from everything. Maybe I should divide by 5 first, whatever. And then we divide everything by negative 5. So negative epsilon divided by negative 5 is epsilon over 5. Negative 10 divided by negative 5 is positive 2. Switch the order of the inequality because we're divided by a negative. And then epsilon divided by negative 5 is negative epsilon over 5. And negative 10 divided by negative 5 is positive 2. So we need x to be between 2 plus epsilon over 5 and 2 minus epsilon over 5. And then the other side of thing is we want the absolute value of x minus 2 to be less than delta. So we say, okay, x minus 2 is between delta and negative delta. Sometimes people write delta 1 and delta 2 because they know that the deltas are going to be different. It's not going to happen here because it's linear. We'll say more about this in a little bit. So then I isolate x and I say that, okay, great. X is between 2 plus delta and 2 minus delta. So then I set, and let me really rewrite this in the same order. Sorry, it's looking terrible. So I say, okay, great. X has to be bigger than this, x has to be bigger than this, so I need these to be the same. And similarly, x needs to be less than this and less than this, so these need to be the same. So I'm going to set 2 minus delta equal to 2 minus epsilon over 5, which means delta equals epsilon over 5. And over here, same kind of deal. 2 plus delta equal to 2 plus epsilon over 5 also gives me delta equals epsilon over 5. So either side of this inequality is giving me that delta needs to equal epsilon over 5. So that as long as to the right of x I'm within epsilon over 5, or to the left of x I'm within epsilon over 5, or to the right of x I'm within epsilon over 5, I'm still going to get my f of x to be within epsilon of the function. But I don't need to do all this work when it's linear because there's a shortcut. You can just do the factoring out and the dividing and it works. That shortcut that we've used twice now doesn't work if things are non. So let's look at a non-linear example. Let's not look at that one. I'm not a fan. Let's look at that one. Yeah. So we want to show or prove, I'm going to keep our notes in order here, that the limit as x approaches 3 of x squared plus 1 is equal to 10. Sorry, you can't see that. I think I zoomed in too much. Yeah, okay. All right. So, same thing we always do. We're going to start by saying I want the absolute value of my function minus the limit to be less than epsilon. And I also want the absolute value of x minus 3 to be less than delta. The idea is that we're going to work with both of these compound inequalities until we can get to isolating x. And then we're going to set the things that are between equal to each other and see what we need delta to be in terms of epsilon. So I'm gonna isolate x here. Okay, let's see. So I have x squared minus 9 in absolute value, less than epsilon, which means I have x squared minus 9 between epsilon and negative epsilon. Add 9. So 9 minus epsilon is less than x squared, is less than 9 plus epsilon. And finally, take the square root of everything. The square root of 9 minus epsilon is less than x, is less than the square root of 9 plus epsilon. I will point out that things would become problematic if epsilon got too large. If epsilon was bigger than 9, we couldn't take the square root of 9 minus epsilon. But you should be holding the idea in your head that epsilon is meant to be a small, much less than 1 typically. On the order of 1/1,000,000th, 1/1,000,000,000th, super duper tiny numbers. Okay, let's work with the other side. The other side's easier. With x minus 3 between. Okay, and I will say it's typical to use delta 1 and delta 2. I typically go, what do I typically do? What did I do last time I was doing this? Good question. Oh, I did this one differently. So I'm gonna say this is negative delta 1, positive delta 2. I do like to still think, I'm still thinking of delta itself being a positive number. So this is some small positive number. This is some small negative number where delta 1 is still a small positive number. The reason we're doing this is because they don't end up being the same. So we don't want to call them the same name if they end up having different values. All right. We do one thing. I'm going to add 3 to all sides. So 3 minus delta 1 is less than x is less than 3 plus delta 2. And before we actually do the rest of this, I might, no, I'll draw the picture after. So then we're going to set these equal to each other. So we're going to set the things that x is bigger than 2 equal to each other. So we're going to set square root of 9 minus epsilon equal to 3 minus delta 1. And we're going to solve for delta 1. So adding delta 1 over here, subtracting the square root of 9 minus epsilon over there. I will point out, because I think it's worth pointing out, this number is a small positive number. Right? If epsilon, right, the square root of 9 minus epsilon is going to be a little bit less than 3, and 3 minus number a little bit smaller than 3 is still going to be positive. Great. And then we're going to do the same thing for the right-hand sides. We're also going to set 3 plus delta 2 equal to the square root of 9 plus epsilon. Solving for delta 2, it's going to be the square root of 9 plus epsilon minus 3. Do be careful. It's really easy to start getting confused just because epsilon and 3 kind of look like each other. I mean, epsilon looks like a backwards 3, at least the way I draw it. So don't interchange your epsilons and your 3s if you've got lots of 3s going on. Let's draw a picture. So here's what we've got going on. Can I draw a good picture? I probably can. Always, every time. So I want to try and draw this. Yeah. I'm going to try and draw it a little bit exaggerated. So here's my y equal to x squared plus 1. Now let's say 3 is right there. And then here is 3 squared plus 1. And then I'm going to add epsilon. Subtract epsilon. And I do want to make those lengths look as close to being the same as possible. So now check this. Let me ask you all a question, actually. Which side of 3, and I know my drawing is not perfect, but think about the fact that this is this polynomial x squared plus 1. Which side of 3 is the steeper side of this graph? The right side of 3 or the left side of 3? The right side of 3. So on the steeper side, you're going to get just as much vertical change over a smaller horizontal distance. Whereas on the left side, you're going to get just as much vertical change over a longer horizontal distance. So if I've drawn this somewhat deep, now I've kind of drawn terribly, in fact, I want to make this left side look a little bit bigger. Should be, if I've drawn it well. So I want to point out that on the right, here's my delta 2. On the left, here's my delta 1. And notably, again, let's zoom in here a bit. Delta 1 is larger than delta 2. Do you actually know which one's larger? Probably not. Is it nice to see which one is larger? I think so. So we want to pick delta so that if x is within delta on either side, we end up getting our y values within epsilon. Okay, so check this out. If I pick the smaller value, everything's good. Because if I go epsilon over 2 to the right, or epsilon over 2 to the left, sorry, not epsilon, sorry, I'm saying the wrong thing. If I go delta 2 to the right, or delta 2 to the left, which is not quite as big as delta 1, I'm safe. I end up in the region of y values that I want to be within. I am within epsilon on either side of 10. But if I accidentally pick the larger of the two delta values, one side will be okay on, but the other side will not. If I go delta 1 to other side, well, I can go that far to the left and that far right. And then I'm going to end up being out of bounds of where I want to be. I'm not going to be within epsilon of 10. So when we get different delta values because we have a function that's nonlinear, we are always going to choose delta to be the smaller of the two. Typically what we write is we're going to say something like pick delta equal to the minimum of these two delta values, of 3 minus the square root of 9 minus epsilon, comma, the square root of 9 plus epsilon minus 3. I will fully admit, to me, that feels a little bit lazy. I'm not gonna lie. We can find out which one is larger without too much effort. Here's how. Pick a convenient value of epsilon. So let's actually write over here. So delta is going to be the minimum of 3. Now, here's what I should really say. If your actual instructor wants you to just do it this way, this is the way you should do it. If they say just say delta is the minimum of whichever two things, that's fine. But I want to point out, if you pick a value of epsilon, it's easy to evaluate one of these things at. You can totally tell which one's smaller and which one's bigger. I'm going to pick epsilon equal to, let's not go too big here, James. Let's say you pick epsilon equal to 5. It's pretty big still, but not out of the realm of reasonable. If epsilon is equal to 5, then our delta 1, which is 3 minus the square root of 9 minus epsilon, is 3 minus the square root of 9 minus 5, which is 3 minus the square root of 4, which is 3 minus 2, which is 1. And our delta 2 is the square root of 9 plus epsilon minus 3, which is the square root of 9 plus 5. Let me ask you, is the square root of 14 bigger than 4 or less than 4? Less. So this is less than 4 minus 3, which is less than 1. So which one's bigger? Delta 1 has to be the bigger one. Delta 2 has to be the smaller one because delta 2 is less than 1, whereas delta 1 is equal to 1 in this particular choice of epsilon, which totally corresponds with what we've already said. Oh yeah, delta 2 is less than delta 1. So in my opinion, I would make you do the work. I'm not a very kind teacher when I'm actually teaching the class. I'd be like, no, you should find the right one. You should pick the right delta. But you could probably be fine with just saying delta is the minimum of the two. So now we've done all the work we need to do. Now we're going to write the proof, right? Because we still haven't written the proof yet. We've just done all the things. So this is where I would say writing the proof is kind of, well, let me write the proof and then I'll say the words. So to prove to zoom back out, maybe. So to prove that the limit as x approaches 3 of x squared plus 1 is equal to 10. Whoops, that's looking weird. We'll do the following. So we're going to let epsilon be greater than 0. Of course, it's always what we're starting with. Then we would say if delta is equal to, you could either say the minimum of those two delta values, or if you're me, you're going to say that delta is equal to the thing that we want to be, which is the square root of 9 plus epsilon minus 3. Then, and here we almost never reconstitute the work we've done. We just state the result. Then the absolute value of x minus the thing that x is approaching, which is 3, being less than the delta that we have there, is going to imply that the absolute value of our function, x squared plus 1, minus the limit, is less than epsilon. Thus, the limit as x approaches 3 of x squared plus 1 is equal to 10. We already did all the math to show that this was true. Now we're just writing it down. Now, what I would say is that I probably wouldn't write this like on a separate piece of paper. I would probably still have all the work I've done shown above. So if someone's actually grading my work, they can see what I've done. But again, you guys are doing quizzes, right? Like in some are, well, some, is one of the classes doing quizzes? No, I'm maybe thinking the other classes. Sorry. I thought no one's doing quizzes. All right. In discussion. Okay. Yeah. And someone's grading those quizzes at some point? Yeah. Okay. So if you had to do something like this on a quiz, I would certainly make sure that I showed this work first, and then after this work, I would write down the proof of my limit. Okay. It's 2:15. We're here till 2:30. Should we do more of these? Are we done with them? Would love to be done with them, but so here's the deal with these. They feel kind of tedious. It's kind of like, and they're kind of like, why are we doing this? Well, because at some level, calculus is really about showing that things actually are what we say they are. And again, I will just say there are other math classes in the upper division range where, specifically the 127 series, where it's a lot of this saying, if something's really close to something else, then something else is really close to something else. That's a lot of what math is, which sounds, I know, not like the most exciting thing ever, but a lot of things are based on just, if something's close, something else is close. Now, we're going to move beyond this pretty quickly. But for now, this is where we're at. So let's do one more, and then we will revisit this if necessary. Yeah, let's look at this example. Let's look at that example. I like that one better. Yeah. Some of these are getting gnarly. Sure, let's look at this one. So we want to prove the limit as x approaches 5 of, let's not get too crazy, James. 15 over x is equal to 3. Oops, again, always with the zooming issue. Sorry. Same idea as before, meaning, so we want two things to be true. We want the absolute value of our function minus the limit to be less than epsilon. And simultaneously, we want the absolute value of x minus 5 to be less than delta. The x minus whatever less than delta part is always going to be easy to deal with. It's really just like 2 steps at the most. You have x minus 5 between, and again, I would encourage you to say this is delta 2 on the right, negative delta 1 on the left. That's how I would always choose to write it, instead of just negative delta and positive delta, because we know that they're going to be different values. They're always going to be different values if you have something non-linear. That's just the way it goes. And over here, oh, and then we would isolate x and say x is less than 5 plus delta 2 and bigger than 5 minus delta 1. So x is either delta 2 to the right of 5 or delta 1 to the left of 5. And then the other side is the side that actually requires a little bit more careful algebra. So I'm still going to start off with just taking my absolute value inequality and rewriting it as between being epsilon and negative epsilon. These are not different epsilons. These are the same. You always want to be the same amount above your limit as below your limit. Yeah. Now what? Good question. So what I would typically see here is I want to get a common, how do I want to do that? There's a couple ways to go here. I'm trying to think about like, which way would I do this really? I would probably get rid of this 3 first. I'm going to add 3 to every side. So 3 plus epsilon is bigger than 15 over x. It's bigger than 3, sorry, 3 what? 3 minus epsilon, sorry, is less than 15 over x is less than 3 plus epsilon. The fast way to do the next part is just to take the reciprocal of every side. When you take the reciprocal of things, what happens to the inequality? Good question. 2 is less than 3. If you take the reciprocal of both sides, 1/2 is bigger than 1/3. So just like when you multiply or divide by a negative number, taking the reciprocal of both sides of an inequality changes the direction of the inequality. You could also do it the longer way by multiplying everything by x and then dividing everything by 15. And it's just kind of a tedious game though. So let's take the reciprocal of everything. So 1 over 3 minus epsilon is bigger than x over 15, bless you, is bigger than 1 over 3 plus epsilon. And then we finally isolate x by multiplying both sides by 15, or all sides by 15. And I'm going to change the way I've written my inequality. So I'm going to write it as this less than that, less than that. So I'm going to say 1 over 3 plus epsilon times 15, so 15 over 3 plus epsilon is less than x, is less than 15 over 3 minus epsilon. And then I'm going to set that equal to that. And this. And then I'm going to try and solve for the corresponding deltas. So I think I have enough room here. 5 minus delta 1 is equal to 15 over 3 plus epsilon. Solving for delta usually isn't that bad, because usually you got something plus delta or something minus delta. It's just like subtracting off that piece. So if it were me, I'd probably add the delta 1 over here, subtract this over there to get the delta 1 is equal to 5 minus 15 over 3 plus epsilon. It's never a bad idea to think about if epsilon's a small positive number, is delta also going to be a small positive number? So if delta is like if epsilon is like 0.1, 3 plus 0.1 is 3.1. 15 divided by 3.1 is a little bit smaller than 5. 5 minus a little bit smaller than 5 is slightly positive. So we're good. We're in the good spot. But it's always a good check to be like, is the thing I'm getting really actually a small positive number? Same deal for the other one. Let's say we have 5 plus delta 2 equal to 15 over 3 minus epsilon, or delta 2 equals 15 over 3 minus epsilon minus 5. 3 minus epsilon, not 3. See, I did it. It's terrible. And again, if epsilon is a small number, 3 minus epsilon is a little bit smaller than 3, and 15 divided by a number that's a little bit smaller than 3 is a little bit larger than 5. And then minus 5 is still slightly positive. And here we could be lazy. We could say, well, we're just going to let delta equal the minimum of those two things. 5 minus 15 over 3 plus epsilon, and 15 over 3 minus epsilon minus 5. You could also make a different choice, right? You could say, or I'm gonna look and see which one's actually smaller by setting epsilon equal to 2. And if epsilon is 2, well then 3 plus 2 is 5, 15 over 5 is 3, 5 minus 3 is 2. And that'd be delta 1. And if epsilon is 2, then delta 2 is going to be 3 minus 2 is 1, 15 over 1 is 15, 15 minus 5 is 10. So clearly this is the smaller choice. And it really does work as long as you're not picking something that's like too far beyond where things might be undefined. Like I shouldn't be picking any epsilon equal to or greater than 3, because that would be problematic. But if you pick an epsilon within kind of the range of reasonability, you can figure out which of those deltas is smaller, which I think is neat, but is probably not super necessary. And then our proof, which I would try to write on the same page if I had enough space, my proof would be okay. For any epsilon greater than 0. That is always the beginning, or let epsilon be greater than 0. If delta is equal to the minimum of those two numbers, so 5 minus 15 over 3 plus epsilon, comma, 15 over 3 minus epsilon minus 5, which again, we know is this one. But you don't have to know that. Saying if the minimum of those two is good enough, then the absolute value of, okay, this is where you're just writing the definition of the limit being what it is. The absolute value of x minus whatever less than delta implies that the absolute value of f of x minus your limit is less than. In fact, you also write that down. Write down the next part. The absolute value of something minus something is less than something. Implies the absolute value of something minus something is less than something. I'll even give you I'll give you the delta and the epsilon. You need to figure out what goes here, what goes in there. Oh, there's a chat. If you guys see a chat, let me know. I have something missing. Can you explain again how I chose 2? So I chose 2, and again, not super necessary, but the way I chose 2 here was I was really looking for a number that when I plugged it into either one of these, my division would be easy. So I was like, oh, 3 plus 2 is 5. 15 divided by 5 is going to be nice. It also happened to work out nicely for the other one as well. But what I was actually doing, or was I making sure I didn't do, is making sure that I didn't pick something that was equal to 3 or bigger than 3. Because if it's bigger than 3, then like 3 minus 4 is -1 and 15 over, that's going to be problematic. This should always be positive. So I need to make sure that I stayed within being less than 3. That's how I did it. And also should be positive. So I was picking something between 0 and 3. But again, you can probably circumvent any of that by just saying, let delta be the minimum of these two things. Yeah. No, it's because it's in the denominator. So like in the previous problem we were doing, I was picking an epsilon that was less than 9 because I had the square root of 9 minus epsilon. If I picked anything larger than 9, then the insides of the square root becomes something that's negative, and we can't do that. So I'm trying to pick something that's just like in the domain of what epsilon has to be so that delta is still defined. So here we should have the absolute value of x minus whatever we're approaching, which is 5, less than delta, should imply that the absolute value of f of x minus its limit is less than epsilon. This is always what we're looking for. And then finally, this proves the limit as x approaches 5 of 15 over x. Sometimes you'll see someone write at the end of this a little box and then they'll like scribble it in. That means like we proved the thing we wanted to prove. I don't know why people do that or why it's come to mean that, but it does. So if you ever see a professor or a TA, so it'd be like a little box and they're like, we proved it. That's what they mean when they write that. Yeah.
You always have to take like a negative epsilon to the outside.
Yeah, so like, yeah, basically when you're dealing with this inequality, this left side has to be equal to that left side, and this right side has to be equal to that right side. It is, yeah. I mean, I could have left it like this, but then I would have been like, this side is that side and this side is that side. I would rather just write both my inequalities in the same order and direction, so I don't have to worry about making sure they match up. Or so I don't have to think too hard about making sure they match up. I still need to worry that they match up, but it's just easier to see it that way. And so then, since we only have a couple minutes left, I'll end by saying just, I'll restate the definition of the limit or the precise definition again. So we say that the limit as x approaches a of f of x is equal to L if for any epsilon greater than 0, the absolute value of x minus a being less than delta implies the absolute value of f of x minus L is less than epsilon. That is the definition of the limit of something equaling a number, is that if this is true, then this is true. And I think I might have forgotten one small thing. I think you're also supposed to say that this absolute value has to be greater than 0. Because remember, when you're talking about a limit as x approaches a, x gets really, really, really close, but not equal to, doesn't actually get to a. That's why we should be saying the difference between x and a is greater than 0, because they're not actually ever equal to each other. All right, so that's the precise definition of the limit, or the delta epsilon proof. Happy to talk about it in office hours or in other venues. I will try not to talk about it too much more in co class, because as much as I might like to, we got other things to do.